Thank you very much for bringing me back to Belgium, my native country. And so it's a privilege to be the first speaker in this school. And so indeed, I will discuss only graph theory in this mini course. And so the topic, the aim is to introduce Ramanujan graphs and discuss how to construct them. And let me start with some algebraic graph theory. So we'll deal with graphs which are simple, unoriented, and with no loop. So such a graph is described by a set of vertices and a set of edges. These are vertices. These are edges. And edges are two-element subsets. And so we have the adjacency relation, which we denote by tilde, and we say that x is adjacent to y, so this means that the subset xy is an edge.
Wait, sorry, what's simple?
Simple means this. you have at most one edge between.
It's like simplicial.
Pardon me?
Simplicial. Okay, yeah.
Simple.
Okay.
She was my student, by the way. And we say that x is k-regular. So if every vertex has k vertices. So k is some integer, which is at least 2. And what? Who disagrees?
K neighbors or K.
That's k. Oh yeah, k neighbors. Sorry. K neighbors. Mm-hmm. And we have the adjacency matrix A, which is indexed by pairs of vertices, and it's a 0-1 matrix, and AXY is 1 if x is adjacent to y, and 0 otherwise. So AXY is a symmetric matrix. A is symmetric. And assuming the graph is finite, so this means by standard linear algebra that A is diagonalizable over the reals. And so basically, if we want to define algebraic graph theory, it's let's say, the study of the interaction between the eigenvalues of the adjacency matrix and the combinatorics of the graph. And notice that the adjacency matrix captures the full information of the graph. If you give me the adjacency matrix, I can recover the graph. And okay, so the following proposition is classical. So assume that x is finite, connected, and k-regular graph. Then every eigenvalue lambda of capital A satisfies that in absolute value is less or equal to k. So this means that the spectrum is contained in the interval minus k plus k. And lambda equals k is an eigenvalue of multiplicity 1. And finally, okay, let me put it this way, minus k is an eigenvalue if and only if the graph x is bipartite. This means also bicolorable. So you may color it in two colors so that adjacent vertices will not have the same color. And in that case, the set of eigenvalues, the spectrum of A, is symmetric with respect to 0 in the bipartite. So in other words, if this is the interval minus k plus k, for a carrier graph, the eigenvalue k is always there. Always. And the other way, and minus k, we understand perfectly when it's there. It's there. If and only if the graph is bipartite, x bipartite. And so this means that the other eigenvalues are somewhere in between. And yeah, it's customary to write the spectrum of A in decreasing order, from top to bottom. So the first eigenvalue, lambda 0 is k. It has multiplicity 1. So then we have lambda 1. So in my drawing, this will be lambda 1. Then comes lambda 2. Well, lambda 2 might be equal to lambda 1 because there might be multiplicity. So that's lambda 1. Lambda, and then we go down all the way to lambda n minus 1. So this means that n is the number of vertices. And this is less or equal, greater or equal to minus k. So that's the spectrum of A. Okay? And now, let me add in my drawing. It should be symmetric. Yeah. Two more values. Here is minus 2 root of k minus 1. And here is plus 2 root of k minus 1. You see that for k equals 2 there is an accident. For k equals 2 they are equal. I mean 2 root k minus 1 is equal to k. So this means that this is why two regular graphs, which are cycles, will be completely forgotten. We'll just mention them as examples. So, but for, let's say that for k it is 3. This is the drawing. And oh, by the way, minus k and plus k are called the trivial eigenvalues because we understand them perfectly. So k and minus k trivial eigenvalue. Definition. We say that a finite connected k-regular graph is Ramanujan if every non-trivial eigenvalue lambda satisfies that in absolute value it's less than 2 roots of k minus 1. So, again, the graph will be Ramanujan if, except possibly for the two trivial eigenvalues k and minus k, all the other eigenvalues will be in between minus 2 root minus k and 2 root of k minus 1. I could end the course here. but maybe the organizers will not be happy. Okay. So, by the way, what is 2 root k minus 1? It's the spectral radius of the adjacency matrix of the k-regular tree tk. So that's for k equals 3. And this infinite object appears naturally because it is the universal cover of every finite k-regular graphs, well, connected k-regular graphs. So tk, which is the universal cover of, let's say, X. And the spectrum of the adjacency matrix of Tk, the spectrum as an operator on L2 of the vertices, was computed by Keston in 1959. Spectrum of k tk, and what he shows is that it's precisely the interval minus 2 root k minus 1 plus 2 root of k minus 1. So this is to give you a meaning of the significance of this number 2 root of k minus 1. And what's the name of the game? What are we after? We are after families of, okay, so Ramanujan graph is something that makes sense for one graph. But the point is that we will be after families of k regular Ramanujan graphs with k fixed. And okay, maybe before going into that, I should give you some examples. So you take the cycle Cn, this would be C6, and as I already mentioned, cycles are the only families of finite two regular graphs, finite connected two regular. Then, if you compute the eigenvalues, you find there are the families 2 cosine of 2 pi L over n, where L goes from 0 to n minus 1. And as I already mentioned, it's trivially Ramanujan. It's Ramanujan for a bad reason. Okay. Let me now switch to the d-dimensional cube. H sub d. So that would be C. So this one is d regular. And the eigenvalues are d minus 2, d minus 4, all the way down to minus d. And you see that because the steps are by 2, this will be Ramanujan only for small d. And more precise computation shows that it's Ramanujan for d between 2 and in my notes 6. And not for higher d. Okay, third example. Let's look at the complete graph. Let's say case of D on D vertices. So this means that every vertex is connected to every other vertex. So 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That would be K5. And then here the eigenvalues. So this one is d minus 1 regular. And the eigenvalues are minus 1 and d minus 1. And so this one will be Ramanujan for every d. And let me give a final example. The complete bipartite graph KDD. So this means that you take 2D vertices, divided in 2. So let me draw for you K33. So, and every vertex on the left is joined to every vertex on the right. That would be K3. And in this, so this one is D regular. And eigenvalues are minus d, 0, and d. And again, it's Ramanujan for every d. And these examples give us a wrong impression that Ramanujan graphs are easy to construct. It's easy to come up with isolated examples, or even examples in families, but if you look at all of those families except for the first one, you see that they are regular, but the degree of the graph increases with the parameter. And so, from chalk, we are after infinite families of k regular with k fixed Ramanujan graph. And that makes the question non-trivial. And okay, no, well, later I will have to motivate the question, why is it interesting? But maybe at this point, let me tell you what we know. So, okay. Move. So, in the first column, I will indicate the regularity k, then who did it, and finally, is the construction explicit or not? And the story starts in 1986 with two papers published independently by Lubotzky-Phillips and Sarnak, who coined the word Ramanujan graph, and then independently by Goulis. And they were able to construct families of k-regular graphs for k of the form 1 plus p, where p is a not prime. And let me also mention they did it for both, they constructed families of Ramanujan graphs which are both bipartite and non-bipartite. And that's explicit. Shortly after, Patrick Hsu treated the case of the oddest prime, which is p equals 2. So he treated the three regular graphs, and that was when in 92, I guess. And again, both bipartite and not bipartite. Then, the case of k being of the form 1 plus q, where q is a prime power. Oh, yeah, and Hsu, that was explicit, sorry. That was treated in 1994 by Morgenstern. And again, that's explicit. And now we jump to 2014. Every k, at least 3. So that was done by Adam Marcus together with Spielman Lubotzky-Phillips-Sarnak, but only for bipartite graphs. And the construction is not explicit. The proof is probabilistic. And so basically that's where we are. So again, we know that there exist families of Ramanujan graph for every k at least 3, but only for bipartite graphs. And it's still an open question to do it for non-bipartite graphs. And again, the defect is that the proof was probabilistic, but however, in 2016, Michael Cohen gave an algorithm to construct those graphs in polynomial time. And I'm not sure whether this holds for explicit or non-explicit. So, the difference is with the previous construction is that, well, okay, you want graphs, I show you the graphs. And here I just show, I mean, there is only an algorithm. Okay. Again, I could stop here. But now, of course, comes the main question, why are we doing that? And I have to now I have to talk about expanded graphs. Expanders. And as I mentioned, Ramanujan can be defined for a single graph. But expanders, the definition of expanders makes sense only when you are interested in families. So expanders are families of finite connected graphs of increasing size. And they satisfy two apparently contradictory requirements. The first one is that they are robust. And by robust, I mean hard to disconnect. So to make them not connected, you must remove a fairly large number of edges. And in the same time, they have few edges. And let's look at two examples to understand what I mean by contradictory. The complete graph, case of D, is hard to disconnect. But in the same time, it has the maximal number of edges, which is, I guess, d minus 1 over 2 edges. Well, if you look at a cycle, Cn, this one is few edges, n edges, but you just remove two edges and you disconnect it. Removing two edges. And okay, so the robustness of a graph with respect to trying to disconnect it is measured by something called the Cheeger constant, or isoperimetric constant. And this is defined as follows. So first, well, definition in two parts. If you have a subset of the vertex set, the boundary of S is the set of edges that connect S to the complement. So connecting S to V minus S. So that we are looking at edges with one foot in S and the other foot in V minus S. And so the mental image I have is the following, that if this is your subset S of the vertex set, you look at edges that cross, that go like this. That would be boundary of S. And you know the Cheeger constant of the graph X, is, oh yeah, I'm assuming that X is finite and connected. So it's denoted by H of X. And it is the minimum of the ratio between the set, the cardinality of the boundary of S and the cardinality of S. And you take the minimum over all sets, well, which are non-empty, and also in the same time not too big, namely they are at most half of the total number of vertices. Okay, so we restrict to those sets because the notion of boundary is symmetric. The boundary of S is the same as the boundary of V minus S with my definition. So remark that the boundary of S is the same as the boundary of V minus S. And the point is, I claim that H of X is a measure. Is a measure of robustness. Of X. And if I revisit the two examples I had over there, so the first one is the complete graph K sub D. If you have a subset with, say, S element, then the cardinality of the boundary is, I guess, S times n minus S, and you see that the Cheeger constant. So So when you divide by the quantity of S, the S cancels out, and you must minimize n minus S with over S less than n, oh, sorry, n is D, my mistake. You must minimize D minus S, and you get that it's approximately D over 2. And for the other example, if you take for x the cycle of length n, c to the n, if I take for s a half cycle, and I get that the Ziegler constant, so the boundary is exactly 2 edges, so the Ziegler constant will be less than 2 divided by n over 2. And so we see that that will be approximately 4 over n. So this goes to 0 for n going to infinity, for n becoming large. The problem with the Ziegler constant is that if you want to compute it explicitly, you see that basically you need 2 to the power n over 2, where n is the number of vertices operations, because here you have 2 to the n over 2 subsets to consider. And the good news is that that quantity can be estimated using the spectrum of the adjacency matrix. 2.2 Ziegler-Boozer inequality. And that's the following inequality. So assume that x is finite connected and k regular. Then you have both a lower bound and an upper bound of h of x. And the lower bound is that it's h of x is greater than k minus lambda 1 over 2. And lambda 1 is the first non-trivial eigenvalue of the adjacency matrix. And this is, on the other hand, this is dominated by square root of 2k times k minus lambda 1. Maybe I should give attributions. The lower bound was proved by Alain, and Vitaly Gilman in 1984. And the upper bound by Joseph Dotchuk in 1985. So then why is it called Ziegler-Boozer inequality? Because it's a discrete analog of an inequality that holds for Riemannian manifolds. And so you may define a Ziegler constant, and that was done by Ziegler in 1970 for closed Riemannian manifold. And Ziegler proved that, obtained a lower bound involving the first non-trivial eigenvalue of the Laplace, of the Riemannian Laplace operator. And some years later, Peter Boozer proved an upper bound involving, that was, in the Riemannian case, it's more complicated because it involves some bound on the curvature, if I remember correctly, on the Ricci curvature of the manifold. But that's why it's called Shiger-Boozer. And now, I tried to tell you, expand this by saying that there's a graph that both robust and have few edges. And, okay, what do we mean by few? Well, we saw complete graphs where the number of edges is quadratic in the number of vertices. And so we are going to restrict to k-regular graphs. We restrict to k-regular graphs because the number of edges of a k-regular graph on n vertices is k times n over 2. And that's the famous handshake lemma. When you count the number of handshakes in a party, you must divide by 2 because shaking hands is something symmetric. And the point is that this is, of course, linear in n, and that's what we are after. So this is what we mean by few edges. And now comes the definition.
I'm not sure I understand the because and the statement.
Sorry?
I'm not sure I understand the because and the statement.
Sorry, there is some noise.
Why is there an explanation for why you restrict?
Because the number of edges is linear with respect to the number of vertices. No, for complete graphs it would be quadratic in the number of vertices. Here is linear, and it's clear we cannot do better.
Okay, that's really clear.
The K is fixed now.
Here are your graphs for fixed case like.
Yeah, we fix k and we let n go.
Yeah. But you could as well consider non-regular graphs.
Not for this mini course. Because it's an introductory mini course. So let xi be a sequence of finite connected k-regular graphs. And you assume that they have increasing size. So this means that the number of vertices goes to infinity for I going to infinity. And we say that this family is an expander. Is an expander if there exists epsilon, a positive epsilon, such that the Cheeger constant of xi is at least epsilon for every I. So this means that the Cheeger constant is bounded away from 0. But by Shiger-Boozer, we see that basically the Cheeger constant behaves in the same way as the number k minus lambda 1. Oh, by the way, k minus lambda 1 has a name. It's called the spectral gap. And so this means that hi hx bounded away from 0 is equivalent to lambda 1 being bounded away from k. So this means, so, like Chigo-Boozer, it's equivalent to the existence of some positive delta such that lambda 1 of xi is less to k minus delta for every. Okay, so that's the definition of an expander, and the mere existence of an expanding family is not obvious. And so the so there is an existence proof by Pinsker, back in 1970, which says that most of the graphs are good. So this means that for every epsilon, the proportion of k-regular graphs on n vertices such that the Cheeger constant is less than epsilon. When you compare it to the total number of k-regular graphs on n vertices, this proportion goes to 0 for n going to infinity. And let me finish by mentioning the link with Indira Chatterjee's mini course, which is that the first explicit construction of expanders is due to Margulis. And that was in 1973. And the tool was Kasdan's property T. So basically, he started with an infinite group having Kasdan's property T. He looked at finite portions. He looked at Cayley graphs of those finite portions for a generating set coming from the group above, and proved that those family of Cayley graphs was an expander family. And I think it's time for me to. It's a good point to stop. Thank you.
Thank you very much for that, for this beautiful first lecture. Do we have questions for that?
Mm-hmm. Yeah, I had one question, but I was too late to ask it anyway. You said that the spectrum of the adjacency matrix of the k-regular tree is contained within the interval of the Ramanujan eigenvalues.
Yeah, exactly. Actually,
Yeah.
it's a whole interval.
Yeah, it's the whole interval. So that means that this lemma of k being an eigenvalue definitely does not hold in the infinite case.
That's
okay.
yeah.
Yeah. That's
nothing
everything.
to add.
Yeah, no, I was just.
Yeah, but you're perfectly right.
Yeah, okay.
And what I can say is that because you work on the Hilbert space L2, and the point is that for a finite graph, the eigenvalue corresponding to k is a constant function, 1. And this one is not square integrable, square summable, right? In the infinite case. That's why it disappears.
And if you remark about the Pinsker result, I think Barshdin and Kolmogorov had in 1967 a similar result for studying the brain.
That's correct. This is something that surfaced fairly recently, around 2000, that And there was a paper in Russian, and so that, and you know, well, it was completely it was completely missed in the West. Yeah. And so there is a paper by what's the first name? Bajdin, and the other one is the great Kolmogorov. And and so they really came up with the definition of expanders. And did they have a construction?
Well, randomly, they showed that random.
Okay.
Just the same as construction? The same construction
No.
as Pinsker?
It's not a construction, it just says that if you take a random one, you'll get an expander. But most graphs are expanded.
I think they
But
were
isn't that
also
what
working
Pinsker
with
said?
directed
Yeah,
graphs.
just earlier.
But it's the same construction.
But not a construction.
I mean, the same kind of.
Same, yeah, same argument.
More questions?
If you want to do this game, then earlier than Chigger and Boozer, Mazia, behind the Iron Curtain, proved this inequality. Before Chigger and Boozer.
Which one?
The one for Riemannian manifold. No, for Riemannian manifold. Before Chigger, no, this is Millman and Doziuk.
No. I mean, okay. So what I said is, I didn't write it, but I said that Chigger proved the lower bound and Boozer proved the upper bound.
And before them, Mazia, I think, proved both of them in Russia. So it's the same story. They always have somebody in Russia who did it before.
Yeah.
What does it mean for Riemannian manifolds? Like, what's the statement in that context? You just said that.
The Chigger
Well,
inequality.
the Chigger inequality is fairly easy to state. So that's if you so you define the Chigger constant by basically you cut your manifold in two by some hypersurface, and because your manifold is closed, right? So you have, let's say, two halves, and you take the Riemannian volume of one half, and you define that high supersymmetric inequality. Well, except that here you have an infinite, right? And then what Chigger proved was that this geometrically defined quantity is larger than I think on the top of my head is lambda 1 over 4. It's a very simple constant, where lambda 1 is the first non-zero eigenvalue of the Riemannian Laplace operator. So d star d, where d is the exterior derivative. And so it was known since Hermann Weil, that the spectrum of the Riemann operator starts with 0, and then it's a sequence of eigenvalues that goes to infinity. And so Chigger was able to compare it to the Chigger constant. In a nutshell.
Does that constant have any connection with k minus lambda 1 over 2 over here, the same way that this definition of H does?
Oh yeah, the point is that again, in the mini course you have to make some choices. I chose to do everything with the adjacency matrix, but there is a naturally defined combinatorial Laplace operator, which on the k-regular graphs is k times the identity minus a. And if you work with this one, then you get you don't get k minus lambda 1 is replaced by the first eigenvalue of that one.
Does that, if you pick a random bipartite graph, does that still have this property? The Pinsker property?
Depending on your measure, I guess. Depend on your
I guess
randomness
so.
measure. It depends on your randomness measure.
Yeah, I guess like.
I guess
I don't know exactly
I
what
guess so.
Yeah, either bipartite random graph, but something similar.
Yeah, I guess so. Yeah. Okay, I would have to check the details. But
Yeah. And today we even know that it's almost Ramanujan with probability going to 1.
yeah, that's Friedman result. Yeah.
Yeah, it's like Bordenave extension of Friedman.
All of the that.
I still have a question about the motivation that you used using the K-regular tree. Well, why does that motivate to look at Ramanujan graphs in the finite case?
Well, I could, okay. One way to answer that comes to my mind is that for the same reason that you can study hyperbolic surfaces by looking at the Poincaré disk, at the hyperbolic plane. On the hyperbolic plane, you have the fundamental group, which is a nice tessellation group of the disk, and that acts, and you can view your surface as a. But that's the uniformization theorem. You can view your surface as a quotient of it. Yeah. Is that good for? Is this good as an answer?
Well, it depends on what it does with the eigenvalues. Is there a connection between what happens?
The point. Oh yeah, but okay. There is this splendid book, which is the only book in my life that I wrote from the first page to the last one. That's a book by Lubotzky. Discrete group, invariant measures, and expanded graph. And he really makes the connection. He really shows how important the motivation was from Riemannian geometry was, and especially there is a chapter on Zellberg's 1/4 eigenvalue, which is the fact that if you look at so-called arithmetic surfaces, so quotient of the hyperbolic plane by arithmetic subgroups of SL2R. SL2R is the group of isometries. It's the nicest group ever. And so if you quotient by if you look at eigenvalue, Zellberg conjecture that all non-trivial eigenvalues of the Riemannian Laplace operator should be at least 1/4, and it's still a conjecture today. And what he could prove is that it's at least 3/16. And when you use this construction in a reasonable way and discretize your surface, you construct families of expanders using Zellberg's result. And trying to improve from 3/16 to 1/4 is still a subject of active research. And well, there was some improvement by Peter Sarnak, for instance. Yeah, okay. But I don't want to spend the whole coffee break on that.
Okay, more questions? It's great there are so many questions. Okay, so thank you again.
Thank you.